Hi everyone, I hope you're keeping well. We're going to do a video looking at the homework for week 2. This is the higher level question and it's from the 2020 paper. It's not, I beg your pardon. Yeah, it's 2020 question 6. So it's the 2020 question 6 question. Just zoom in a little bit here. I'm not sure how visible it was earlier. Let's see if this helps. Okay, so I'd like you to remember that you've access to all your notes and stuff before tackling these, okay? So revise away. Before just jumping into the question, go through the notes I gave you on the mechanics section, go through your own notes, go through the textbook, watch the videos or video and this video for the, before you hit the next question. And have your log tables beside you when you're doing the question, okay? To give every part of it a go, all right? Like, don't just leave it blank, give it a shot. Worst case scenario, you get it wrong. Do definitely give it a shot. Okay, so let's get cracking. This is question 6 from 2020. It's a mechanics question, which is where we're focusing on with our revision right now. So the first part is state Newton's laws of motion. I won't write them out in detail, I'll just say them verbally. The first one is that an object at rest or an object will remain at rest or in constant motion unless an external force acts on it. So if forces are balanced on an object, it will either be stationary or moving at a constant velocity. The second rule is that the force applied is proportional to the change of momentum. We're going to revisit that in part 2 in a moment, where we have that derivation cropping up again. And the third one is for every action there's an equal and opposite reaction, or a bit more verbose. When body A exerts a force on body B exerts a force equal in magnitude but opposite in direction on body B. The other one, A on B means B on A. Okay, so there's the 3 laws. I'm not going to write them all out. They're in your notes. They're in the summary sheets I gave you. They're in last week's video. Let's get on to kind of slightly trickier stuff. Okay, so show that F equals ma is a special case of Newton's second law. Now again, this is a derivation. It's on your notes, but I will go through this real quick. Basically, because a lot of people struggled with this last time, they want us to get to F equals ma, which is a special case of the second law of motion, which is that the force is proportional to a change in momentum over time. Okay, so this is what we're going to start out with, and we want to get to here. So let's start off by taking out m from the common factor up top there, v minus u over t. Okay, let's just taking the m out. And because v minus u over t is acceleration, that's final velocity minus the change of velocity over time, we can put in a instead of this. So we have F is proportional to mass times acceleration. And then the final kind of couple of steps to make it an equation rather than a proportional relationship, we have to introduce the constant of proportionality, the k. So F equals kma. And because from the definition of the Newton, because 1 Newton is a force that gives an object of 1 kilogram an acceleration of 1 meter per second squared, k equals 1. That gives us F equals ma. So that's sorry, I went off the screen there a little bit. That's the derivation they're fond of asking. It comes up regularly enough. There's a few that we have to kind of learn off, and this is one of them, or at least be able to explain. So that's part 2. There's a decent chunk of points in those two, guys. And that's stuff that's really kind of straightforward enough to memorize. That's like 20 out of 56, relatively handy to get. And then they're going to get more challenging as the question goes on. So let's have a look at part 3. Describe an experiment to find the resultant of 2 coplanar vectors. Okay, so this is when you've got 2 vectors, let's say one there and one there. V is called V1 and V2. What's the resultant? So if you imagine this being a force pulling something in that direction, a force pulling something in this direction, the actual object's going to go like over there somewhere, right? Now, how do you find this out? Or how can we show this? Well, in the experiment, it's the one where you get the 3 Newton meters and you tie them to piece of string with a knot in the middle. I'm doing this very quickly, so it's obviously not going to be a work of art here. Let's call it N1, N2, and N3. So if you've got the forces balanced in this, and I know I've just sketched this, so it doesn't look like we'll just move this guy over here a little bit. Makes it a little bit more straightforward. Okay, so if the knot here is stationary and not moving, it means the forces acting on it are balanced, which means that the resultant of any 2 forces is kind of the other one. So what I mean by this is, if you imagine that this bottom Newton meter just disappeared, right? where would the knot go? Well, this guy's pulling it in that direction. This guy's pulling it in that direction. It would go up like that. But it isn't because of this the tension in this third Newton meter. So the resultant of these two is equal to the reading on the third one, but just in the opposite direction. So this is pulling it down in this direction with a force equal in magnitude to the resultant. So the resultant force is the magnitude on the third Newton meter and in the opposite direction. Now, guys, I'm going to say this once. I'm kind of tired and probably could explain that a little bit more coherently in class, but that's the experiment. We've done it before. It's a matter of just kind of revising it, okay? So the resultant of the two vectors in this case is the magnitude of the third and in the opposite direction. So that's part 3. Okay, part 4 is getting onto a few practical parts and calculations and applying it. So it's about a cricket player. A cricket player moves her hands away from the motion of the ball as she catches it. Use Newton's laws of motion to explain why she moves her hand away from the ball. Now it's actually referring to the second law of motion here, that the force is proportional to mv minus mu over t. So that the change of momentum over time, the rate of change of momentum. Now what this means is if you increase the time of an impact by making t bigger, the overall force goes smaller because you're dividing by a bigger number. So if you stretch out the time of an impact, the force is lessened. So this is the basis on which most of our car safety devices work, like airbags stretch out the moment of impact for your head, so you're not getting the full force. Same thing with seatbelts. They don't stop you suddenly, they stop and slow you down. So it's about stretching out that impact to decrease the force. And when the player catches the ball and moves her hand back, it's the same thing. She's trying to stretch out the time of the impact so it doesn't impart as much force to her hand and it doesn't hurt her as much. Okay, that's part IV. Part IV, and then we've got kind of SUVA type stuff. Okay, now again, on the higher level, often you might have to resolve a vector into its perpendicular and parallel components. Now what do I mean by that? Let's say we've got this vector here, and we might as well keep it relevant. That's the 28 meters per second vector that she's throwing at 45 degrees to the horizontal, okay? So that's 1.6 meters above the ground. That's just showing that it's throwing from her shoulder height. And we'll worry about that 1.6 in a few minutes. Let's just ignore that for now and just look at the vector. So it's a 28 meters per second at 45 degrees to the horizontal. So some of that vector is vertical and some of that vector is horizontal. And we need to break it down into its constituent components. So how much is vertical, how much is horizontal? So let's get the vertical first. So this is the initial velocity, so we're going to call it u. Let's call it a little subscript v for vertical. How do we get it? Well, we multiply the magnitude of the vector, 20 meters per second, by, for vertical, it's by the sine of the angle. In this case, that's sine of 45 degrees. And the horizontal, which we'll call it UH, is 28 meters per second by the cosine of 45 degrees. Now, because this is a 45-degree angle, they're actually going to work out as being equal in value. That's not always the case, so be aware you might get different ones depending on the angle. It just works out quite nice in this one. So 28 times, let's go for vertical first, because that's what we're going to be dealing with, is how long is the ball in the air, times 45. Quick point, make sure your calculator is in degrees and not in radians. And we've got 14 root 2 is the answer in meters per second. Now, if I press the SD, that'll give me the decimal value of it, but we may as well just keep it as 14 root 2 for now, because we're not losing any accuracy there. So in both cases, this is 14 root 2 meters per second. Okay, that's the exact value. We don't need to lose any precision quite yet. Always give her units, and now we've broken our vector into a horizontal and vertical component, and we can see what's going on. So what's the question actually asking us? She then throws the ball upwards with initial velocity of 28 meters per second at 45 degrees to the horizontal. Her hand was 1.6 meters above the ground. A short time later, the ball was caught by another player. When it was caught, the ball was again at a height of 1.6 meters per second. 1.6 meters, I beg your pardon. How long was the ball in the air? Calculate how long the ball was in the air, the horizontal distance travelled, and the maximum height above the ground reached by the ball. Okay, so let's deal with how long the ball was in the air. So very similar to the question in the last week's paper. Excuse me. If you imagine you're looking at something from the side and it's going up. So the ball's going up and then down. So it's going in a parabola like that. We're only interested at the moment in the vertical component. When does it kind of land again? Now again, we'll deal with this 1.6 thing in a moment, which is saying that your starting point is 1.6 meters above the ground in both cases. But we'll add that on at the end. Problem solved. Okay, so we want to see how long is it in the air for. This is going to be a SUVAT question. So let's just write out SUVAT. And we're dealing with the vertical. How long was it in the air for? So let's deal with that first. So we don't know S. We don't know how high it went up. Not quite yet. We know U is the vertical component of the vector, which is 14 root 2 meters per second. Now, let's think about the final velocity. I'm not looking for down here. We're looking for the apex, when it's right at the peak, when it's gone all the way up. And when it's gone all the way up, it's no longer going up, but it's not yet started to come down. All right, its acceleration, it's being accelerated downward the whole time, but its velocity is it's going up, and then it just pause. No, it doesn't even pause, but it's going up, and then it stops going up, and then for a split second before it goes down, its velocity will be 0 meters per second. It's neither up nor down. The acceleration, we've got to be careful here. If the upward direction is positive, that means the downward direction is negative, so our acceleration due to gravity is minus 9.8 meters per second squared. All right, now what are we looking for here? We're looking for the time the ball was in the air. So let's just write out our equations. We've got V equals U plus AT, S equals UT plus half AT squared, and we have V squared equals U squared plus 2AS. So how we do this is we're looking for one of the equations that has the three things that we know and the thing we're looking for. And we're looking for, in this first one, time. How long was the ball in the air? So we need an equation that has a U, V, and A in it, and also a T. And it's actually going to be the first one here. That's going to be our one right here. So V equals U plus AT. So when you've chosen which equation you need, just write it out before you put in any values. And then we're going to sub in the values and see what we get. So V is going to be 0. So this is just 0 is equal to U plus AT. Let's bring the U across. Minus U is equal to AT. And now let's put in some numbers. Well, actually, before we do it, let's bring that A across. Minus U divided by A is equal to T. Okay, well, minus U was minus 14 root 2. We'll leave out units for now until we get to the end. Divided by, and remember, minus 9.8. So the minuses are going to cancel, leaving us with a time value of, now I've still got it in my calculator, which is better than rounding it off. I'm going to have 14 root 2 divided by the 9.8, and now I'll round it off a little bit, 2.02 seconds. We're going to have to be careful here. So the 2.02 seconds is when it reached the top of its drop, or of its arc, and then it's going to take another 2.02 seconds to go back. So times 2, the total flight time was 4.04 seconds. Okay, so that's how long the ball was in the air. That's part V. The horizontal distance traveled. Okay, well, let's just get what we need from here. Now, we don't need to do a full SUVAT on this, but you can. But really all we're looking for here is displacement is equal, sorry, let's do it from scratch. It's velocity. Let's look at what velocity is. Velocity is displacement over time. And this time we're looking for horizontal distance, so we're looking for displacement. So the displacement, the distance it travels, is equal to how fast it was traveling times how long it was traveling for. So we have the velocity as our horizontal component. So in this case, they're both the same, but be careful you choose the right one when you're doing this on a question with a trickier angle. So 14 root 2 is the velocity. Multiplied by the time, so that's meters per second, multiplied by the time of 4.04 seconds from the previous, sorry, went off the screen there a bit, from the previous answer. So here I've got my 2.02, let's double that. We're going to have a little bit of rounding error, depending on if you round it off to 4.04, but that's it times 2, and we're going to multiply that by the velocity, which was 14 root 2, and that gives us 80. So it travels 80 meters. Okay, so that's the horizontal distance. Now the final bit, the maximum height. Okay, well, let's go back to the vertical. So we're going to deal with the vertical axis. Now we've got, let's do a SUVAT again, SUVAT. We know that the flight time when it reached the apex was 2.02 seconds. Acceleration was minus 9.8 meters per second squared. The distance is what we're looking for. The initial velocity was the vertical component this time. And again, it's the same, but it's not always going to be. So the vertical component is our 14 root 2 meters per second squared. Or meters per second, sorry guys. And the V was 0. So we're looking for, again, what is the displacement when it's at the peak of that throw. So we have V equals U plus AT. We have S equals UT plus half AT squared. And we have V squared equals U squared plus 2AS. Now remember, you don't have to memorize these, you just have to be able to find them fluidly in your logbook. And if you're doing these questions, make sure you have your logbook with you, because that's the information you have available on the day. Okay, so we're looking for S, and we can use anything that has an S in it, because we've got all the other information, but let's use this guy here. So the displacement is UT plus half AT squared, which is 14 root 2 times 2.02 plus half. I've got to be careful here with the sign because it's minus 9.8 times the time squared, which is 2.02 squared. We're going to just work out what that is. So let's go 14 root 2 multiplied by 2.02. Let's get some brackets going on to keep this a bit more straightforward. That's the first chunk. Plus half multiplied by 9.8. Now that, let's just deal with the plus by minus. There's going to be a minus here. So this, because the acceleration is negative, this is going to work as being minus half times 9.8 times the 2.02 squared. Hopefully I've done enough close brackets there for this to work. And let's just look at our answer here. I don't know if, sorry, I was looking away from the camera there. I'm not sure if that was visible, but it's 14 root 2, the velocity times the time. Acceleration is negative, so it's minus 0.5, that's the half, 9.8 the acceleration due to gravity, and 2.02 is the flight time squared. And it gave us 19.99 meters. Now that makes sense, okay? As for somebody throwing a ball, 20 meters up that's reasonable, all right? If you got like 300 meters or 200 meters or 2 kilometers, then something's going to wobbly. But 20 meters is a nice, believable kind of number. Now let's go back to the little tricky part they threw in. We're looking for the maximum height, and remember, it was thrown from 1.6 meters above the ground. So all you got to do is just add on the 1.6, and it's going to be 21.6 or 21.59 meters. That's your final answer for that one. Okay, long road, guys. We're almost there. Let's do the last one. Any room in the back of this? There is. Okay, so draw a diagram to show the velocity and acceleration of the ball when it is at its maximum height. Also show the force or forces on the ball. Use the letters V, A, and F to label your vectors. Okay, so at the top of its throw, so let's just draw a ball here first. The only force acting on it at its apex is the force of gravity, so it's the weight of the ball. I'm just going to check the marking scheme to see if they're going to be pernickety about the difference between force and gravity here. Just give me one sec, guys. I don't want to send you down the wrong road here. Let's close that. Should recheck the other numbers we got as well. 19.8 horizontal distance, 21.6 vertical. That's all good. Okay, so yeah, the weight going down. Excuse me, and the acceleration is also caused by gravity, so that's going down. And then we've also got horizontal velocity because it's going across. So essentially the ball's reached the top. It's still moving horizontally from left to right from this perspective, but it's being accelerated down by gravity. And the only force acting on it really is the weight. There's going to be marginal air resistance kind of working against it, but really weight is what you're looking for there. Now, bit of a long one. I'm going to stop talking at you because I'm tired. I'm kind of more prone to making mistakes, but hopefully that was helpful. And remember, watch this one and the previous one before trying the next homework question. Or any questions on this, don't be afraid to come to me in class, okay? Or send me a message on Teams. Alright guys, take care. Bye-bye.